Welcome back. Welcome back to our new lectures in high voltage protection relay. In the past few lectures, we introduced the differential protection relay concept. We did differential protection for single phase transformer. We determined the CT ratio. We determined the errors possible, the percentage differential slope, characteristics, and then we did a three-phase transformers using percentage differential relay concept, and then we did multiple examples. Today we are going to talk or to start the protection of a BusBar. Before we start, what's a BusBar? I have a substations. Let's assume I have a substations. This is a substation boundary. This substation is, for example, 132 kilovolt. 2, that will convert to 11 kilovolt. I have this substation. We'll take the 132 kilovolt and then we'll distribute it through 11 kilovolt. Could be 33, could be 66. Any voltage they require. Okay. I have multiple transmission lines. I have transmission line 1 coming up. I have transmission line 2, this all 3 feeders. I have another transmission line, I have another transmission line. All these are 132 kilovolt. To transform from 132 to 11, I should have a transformer. Maybe 1, maybe 2 transformers, maybe 3 transformers. Let's say this is transformer 1, this is transformer 2, depending on the size of your substation. The number of transformers, the number of feeders of transmission line would vary. How do I connect this to this? And then, for me, I could have feeders 1, output 1, 2, 3, 4, 5, 6, 7, 8, whatever numbers is required. How do I connect this? That's where the BusBar role comes in. So, for example, this will go into A. I have a circuit breaker, circuit breaker, circuit breaker, circuit breaker. This is A circuit breaker. From this circuit breaker, I can take it to a bus. And from a bus, we'll go to my transformers. Same for this one. I can have a circuit breaker. Then I could have a bus. This is a 3-phase bus. This is 132 kilovolt bus. This is 11 kilovolt bus. Now, this BusBar is all the same as what we did with BusBar. Can you see the connection in here? You can have a circuit breaker that connect, and could have a circuit breaker that connect down. Any issue? Let's take a moment to read this. This shows us the importance of the BusBar. Now, in an advanced system, I could have a circuit breaker in here. I could have a circuit breaker in here, for example. I could have a circuit breaker in here to make bus sections, which is we will discuss in details. Okay, let's now start from a high level perspective. So, if there's any fault in the BusBar, let's say here I want to put another system. For example, if I have any fault in the BusBar, if I don't have a BusBar protection, what will happen is the ends of the transmission line must trip to isolate the fault. This will cause for my entire system, if I have no protection on the BusBar and all this BusBar are fed by this, and this, under a BusBar fault, if I don't have an adequate bus bar protection, the end will switch. By switching the end, I'll lose everything. That's why the importance of the bus bar, it links. The importance of the bus bar is because the bus bar link different apparatus to different transmission lines. That's why it's very critical for me to protect it. One more element I need to notice, that if my system gets very, very complex, my system gets very big and very powerful, the end of the transmission line will be very difficult for its protection at the end of the terminal, remote ends, for the remote ends to see all the faults in here. That's why bus bar protection is very, very important. Is that clear? Is that clear? Now, the most common used one, protection, the most common used type of protection for bus bar is the percentage differential, or the differential concept, differential relay, where it relies on a CTs, where it does rely on a CTs. I hope that clarified the importance of a bus bar protection and why it is very critical and important, because if there's no protection for the bus bar, for a bus bar fault, you need the remote end to trip. By tripping the remote end, I will lose the entire system. Or I can have a bus bar protection under fault. I will isolate the bus bar section, the under fault, and eliminate any risk of losing my entire system. I hope that's clear. Now, for a differential protection, the differential protection is more straightforward for a bus bar than a transformer. Why? Because I have the number of variables are reduced. The number of variables are reduced. For example, do I have mismatch ratio? Do I have ratio for the transformers? No, the bus bar does not have a ratio. Same voltage goes in, same voltage at this point. Same voltage at this point, same voltage at this point. The whole bus bar will have the same voltage level. Do I have a change in angle, phase angle? Remember, in a transformer, between delta and Y, I have a phase shift of a 30 degree for an angle, for a current. The angle for a current has a shift by 30 degrees between delta and Y. If this is delta, this is all delta. In order for me to connect between delta and Y, usually use a transformer. Let's say this is my transformer, for example, delta Y, or Y delta. But for a bus bar, there will be no phase angle. Also, there will be no rush current. It's not based on a magnetic circuit. I hope that clarified this. Now, there is a major problem. There is one major problem that we are going to discuss in this session when it comes to the bus bar protection. One of the major problem is the unequal core saturation of the CTs. Unequal core saturation of the CTs. Now, the differential protection is based on installing CTs on every phase. One CTs per phase. The CTs, it's a current transformer. It's based on a magnetic circuit. As we discussed in a previous chapter, I could have any magnetic circuit could go into saturation. Now, unequal core saturation of the CT. This unequal core saturation of the CTs, this uncore, is due to the possible large variation in current magnitude and residual flux in individual transformers used in the system. I have individual transformers. Like I said to you, I could have 232 kilovolt to 66. I could have 332 kilovolt to 11 kilovolt. Depending on the size of my substation, I could have multiple transformers. And this possible, that's why, because it is possible to have a multiple number of transformers, the current magnitude and residual flux in individual transformers could impact on the saturation of the CTs, which will have unequal saturation of the CTs. Is that clear? I hope that clarified a couple of points. Protection of a bus bar, it's very important, as we discussed. CT differential protection, it's easier. It's more straightforward. Remember, no inrush, no ratio, no shift angle. I have a problem, unequal saturation of the CTs, due to the current magnitude and the inrush and the residual flux in individual transformers. So unequal core saturation of CTs, of the CTs. Let's now talk about the type of differential protection. Percentage differential relay. Percentage differential relay. Look, I have a bus bar. I want to use 3 transmission line. I have this, my circuit breaker. I have another one with another circuit breaker. I have another one with another circuit breaker. Each one of them, each system is a 3-phase system. Each system is a 3-phase system. Okay. Each phase, 3-phase, 3-phase, 3-phase. So for this system, I need 3 CTs, 3 CTs, 3 CTs. Okay, great. Now let's take as a 1-phase. I'm doing the design now for 1 phase. What do I have to do is I need this is the CTs. These CTs have to go. This one has to go. This will go to relay that have restraint and operating circuit. Into this one, this. Relay this doesn't need it to be that long. This is the circuit. This is restraint. This is the operating. And this is your system. So as you can see, same for the transformer. The CT ratio will be determined based on the rated condition of the system. Same concept. The summation of all this, the vector, the summation of all this must be equal to 0, taking into consideration the angles. However, there is no shift angles in this case. They all will be. There's no shift angle. So whatever you calculate, you calculate. The vector, whatever you calculate, you will use. There's no delta y change for it to happen. Now, is that clear? Before we move on to the next stage, let's take a 10 seconds to digest this information. How did I sketch it? How did I connect it? Remember, this is a 3-phase system. So in here, this is a 3 CTs. 3 CTs. They're all connected. Remember, every phase A, this is phase A, for example. I have phase B, I have phase C. Okay? Now, even with the use of the percentage differential relay, the problem of the completely saturated CT for a closed-in external fault still exists. Even I'm using this system, if I have an external fault very close to the CT, I still have the problem of the saturated CT. CT will go under saturations. So for the bus bar, even if I have an external fault, not a bus bar fault, but however the fault is located close to the bus bar, I still have the issue of a CT going into saturation, which could lead to misoperation of my protection and cause me a major problem. To overcome this problem of saturation for a closed-in fault. To overcome this problem, I have to use, especially in an extra high voltage system, an extra high voltage system could be 132, 330, 500 kilovolt. I have to use a high impedance voltage differential relay called high impedance voltage relay. High impedance voltage relay. So let's talk about this high voltage impedance relay. Remember, this percentage differential relay is same as what we did in the transformer. However, it is more straightforward. Great. So now, we are looking at a high impedance voltage relay. I want to use high impedance voltage relay. What's a high impedance voltage relay? Let's sketch the circuit of a high voltage impedance relay. I want to use the same example as before. This, I have a bus bar. I have a bus bar. I have these feeders are coming in. So as I say, let's consider I want to analyze. Let's consider I am going to analyze phase A. How many circuits do I need? I need CT, CT, and a CT. Pay attention. Let me get a different color pen. Pay attention on this. On this side, I have a variable resistor. This is a variable resistor, and then overcurrent relay, instantaneous overcurrent relay. This is variable overcurrent relay. And what do I put in here? I put a capacitor and inductor. I put a capacitor and inductor, and then in here I put this. And I put the other. Let's make it a little bit higher. Okay, and then this will pay attention to this. This, it's going to go like this. The system in here. The relay design is to overcome the effect of CT saturation and calculating the error voltage across the operating coil. So the whole idea now, because of this issue of saturation, especially under extra high voltage, we designed a high impedance voltage relay where there's a variable resistor, overcurrent relay, you have a capacitor, inductor, diode, and this is your over voltage. This is your over voltage relay. This is your over voltage relay. This is your overvoltage relay. Now, how does the relay operate? The relay discriminates between internal and external fault by the relative magnitude of the voltage across the differential junction point. How does the system work? How? All it does is discriminate between the voltage magnitude across a differential junction if the fault is internal or external. We are going to see an example. So this is what's a high impedance voltage relay. That's what's a high impedance voltage relay. Great. Variable resistor, you all know what a variable resistor is. Overcurrent relay, instantaneous overcurrent relay, we discussed it in 2 chapters before. Why do we have LC circuit? Why? The LC circuit that was put in series is tuned to 50 Hz or a 60 Hz depending your system frequency. I'm working in Dubai, it's a 50 Hz. If I go to the state, to United States, it's a 60 Hz. What does this do? Why do I tune the system to 50 or 60 Hz? To prevent the overvoltage relay from misoperating on a DC offset or harmonic. The LC act like a filter. I wanted to tune it to 60 or 50 Hz to eliminate the operating of my relay under harmonic conditions, misoperating under harmonic conditions, or on DC offset. Perfect. So why is the overcurrent relay? Why the overcurrent relay? This circuit have the potential to reduce the speed of the operation. Therefore, the instantaneous overcurrent relay provide fast tripping for high current fault. This system will reduce the speed of the relay. That's why I use an instantaneous overcurrent relay to give fast tripping under high fault current. Under high fault current, this is my system. I hope that's clear. What's a high impedance voltage relay? In the exam, I could ask you to sketch high impedance voltage relay and explain each component. So why do we use overcurrent relay? Why do we use overcurrent relay in the system? Why we use L and C, and what does it do? Your answer will be that you have to tune, we will tune L and C to 50 or 60 Hz depending on the system. The instantaneous overcurrent relay will be used for a fast tripping under high fault current because this setup reduces the speed of the relay. I hope that's clear. Now, let's put some circuit analysis. Remember, as an electrical engineer, I need to be able to take this setup, put it into circuit, so I can do circuit analysis and come up with my numbers. Remember, previously, we used to do setting for the current. I set my current, for example, ID is KIR, or 0.25. Now I need to determine the voltage, because remember, for high impedance voltage relay, it discriminates between the voltage level if I have an internal or an external fault. Okay, let's just sketch a circuit. That's simple circuit. Simple circuit. BusBar has one input, one output, and see how the circuit analysis looks like. Okay. So in my system, I'm gonna have one BusBar, 3-phase BusBar. I will have, and I am going to have another. Okay, this is my system. So how do I connect? Remember, let's analyze phase A, 3-phase. I have one circuit, one CTs, another CTs. This CTs will go like that. This CTs will go into a whatever relay. Okay, is that clear? Let's talk about, this is my IA. Let's take it as first as an internal fault. If I have an internal fault, this will feed IA this way, and this also could feed IB this way. You know, I could have a voltage coming from here, voltage from here, to contribute to an internal fault. Okay, let's first sketch the electric circuit. Let's sketch the electric circuit of the system. Number one is, what's an electric circuit for me? How do I represent? I have the CT, this in here is, number one is, this it's equal to IA over N. This has a number of N, this will have a number of N. And when I do rated system, when I do example, you will see that this N and this N equal. Okay? When we do an example shortly. Now, this is the output of the secondary current of the CT. The secondary current of the CT that goes in here, it's IA over N. N is the number of turn of the CT. Okay, great. Then, remember I have this. I have X of the excitations. I have the CT excitation reactance. This is the CT excitation reactance. This will go down. Then I have two resistors. This, the CT, this I want to call it RSA, RLA. This is the CT DC winding resistance. This is the DC for the CT. You know the CT made of winding, DC winding resistance. Resistor. Okay, and then this is a cable. I have a cable that connects to a relay. This is the DC resistor. This is the DC resistor, the CT cable DC resistor. This is the DC resistor for the CT cable. After this, it goes into here, where I have XD, where I have ZD, which is the impedance of the differential relay. I have ZD. And then similar on this side for this. So similar on this side, I have this, I have that, I have another one. This one goes down. And I have in here this is XEB, call it this is XEA. This, the system, this one is the CT excitation, this one is the CT excitation of this CT. This is the CT excitation of that CT. This, call it RSB, RSL. This R is the DC windings resistance, the winding, resistance, DC resistance, and this is the lead DC resistance. Is that clear? Each component. This could be an exam question as well. Quiz question. Sketch, I give you this one, and I ask you, sketch the electric circuit and analyze it. Now we're going to analyze the circuit. I hope that's clear. How do I convert from this to this? Let me repeat it one more time. I have one CT, I'm analyzing one CT. Remember, every phase the same, phase A, phase B, phase C. I have one CT, one CT. The first CT is represented by a current and the CT excitation reactance. And then I have a DC resistance of the coil plus the CT DC resistor for the cable. The second, then you have a ZD on this side. Is that clear? Then I have the impedance of the differential branch. This is the impedance of the differential branch. Everything has an impedance. Everything has an impedance. So this impedance in here. And then on the other side, I have the windings, DC. Then I have the cable DC resistor, winding DC resistor. And then I have the CT excitation reactance. And then IB, sorry, this must be divided by N. That goes. Let's sketch now the circuit without all this so we can analyze the circuit. So, to analyze the circuit, let's sketch again the electric circuit. I have this is I, the first one divided by N. I want to call this X E1. I want to call it, this is I1, CT1. This is for CT1 on the primary. Then I have two resistors. Then I have a ZD. Then I have another two resistors. And then I have the excitation for the second one, and this IV over N or I2 over N. This is called RS1, RL1, RL2, RS2. This represents the CT, the second CT. On the second CT, resistors for the lead, DC resistor for the winding, the CT excitation reactance, this for CT1. Now, let's discuss for an internal fault. N is the number of CT ratio. Let's discuss for an internal fault. For an internal fault, as we discussed, both of them will go in. Both will go in. Now, this X and a Z and an X are very large. And now look, I have this goes in. So it will force the current to go IA. So now I have into my system, I have I1 over N and I2 over N will be forced into this high impedance values. Will be forced through the last impedance value, which will cause, when I force a current to go into this high, now X E1, X E2, and ZD are very large. Are very large in magnitude. Because I have an internal fault, both this system goes in, it will force a current. It will force a current to go into XE1, XE2, and ZD. So basically, this current will be forced to go into here. This is my important, this is what my interest. I force some current to go into through the impedance, which is cause high voltage to develop across the differential branch. And then, hence, the relay will operate. Because now I have a high voltage, hence, the relay will operate. This is for an internal fault. What will happen when an external fault? Remember, let me remind you, this was your system. If I have a fault in here, this current and this current. Can you see one of them? If I use nodal analysis across this node, if this is I1, this is I2, I have I1 equal to the summation of all the current is 0 minus I2. Summation of all the current is 0. Is that clear? Is that clear? Remember, I'm looking at it from the secondary side of the CT. Remember this? I look at it from the secondary side of the CT. If a fault happening here, what do I have? I have IB over N, or I2 over N, or I1 over N. It's equal to I2 over N. I have a minus value. Remember, I look at it from a differential perspective. I'm differentiating between the two currents. Be careful, keep this in mind. Differentiate the two currents. Previously, I was adding. See, both of them were adding to it. Now, one will go, one will go out. Is that clear? So in reality, this will go in because these are high, this will go out. So in reality, I'll have almost, in theory, 0 volt drop across my relay or my terminals. 0 volt drop across my terminals. That's why the relay will not operate. I hope that's clear. Remember, I look at it from here from a differentiating point of view. Difference relay. Is that clear? Is that clear? Okay. Let's do an example. Let's do put some numbers. Let us put some numbers. Let us put some numbers. I have a BusBar. I have a 3, 1, 2, I have a 3. I have a CT, and a CT. Each CT is 100 to 1. That's 100 to 1. That's 100 to 1. Under an external fault, is a fault in here. I have this current will contribute by 2000 amp. This will contribute by 4000 amp. This will contribute by 4000 amp. This will contribute by 1000 amp. This will contribute by 1000 amp. I have the lead. It's being given to me that the lead DC resistance and the winding resistance, all this in series, are combined to be 2 ohm. So how do I sketch my circuit? How do I sketch my circuit? Also, it's being given to me that ZD is given to be 2600 ohm. ZD is given to be 2600 ohm. All I do now is let me sketch my circuit. Let me sketch my circuit to determine what is it. Okay, let's sketch the circuit. As I did before, what do I have? I have one like this, then I have this. Remember, I have 2 on this side. See, these 2 will goes into here. Is that correct? These 2 fault goes into here. This fault will goes into fault. So I want to do these 2 in parallel when I come to end this, because remember, I look at it from a differentiation perspective. And then I will goes into like this, put into here. In here, I will have my relay with my resistors, with everything. This is my relay system. Now, what's this current? 2000. I have a CT. The secondary of the CT is 2000 is 20 amps. This current is 40 amps. This is 2 ohm. This is 2 ohm. This is 10 amps. Look, guys, when I have an internal fault, what happens is I have this current goes in here is 70 amp. I have a current goes into here is 70 amp. I have 2600. So now the voltage developed, it's a 70 multiplied by 2600 amps, which is equal to so I'll use a straightforward calculator. 2600 times 70 will give me 182 kilovolt is being developed across the relay. Across the relay is I have this current and this current. All is going to be forced to go in. Where? It cannot go anywhere. Has to go close the loop. Is that clear? That's why I create a high voltage. If there is a fault in here, pay attention now. I hope that's clear. Let's take a moment before I delete this section. Let's take a moment to digest this information. So remember, all I did is these two relay. Remember, I'm talking from a CT perspective on the secondary. I have this goes up from here, this will goes up. This one will give me 20 amps under fault. Under fault condition will give me, this will give me 40 amps. This will give me 10 amps. And because they're all in the same directions, guys, that's why it's going to go in. So we'll add 10 plus 40 plus 20 will give me 70. It's already been given. The relay, the impedance is 2600 ohm. Okay? In this example. Is that clear when it comes to internal fault? Let's look at the external fault. Pay attention to this. Let me use the red pen. Under external fault, pay attention. If I have now the fault is in here, this current now will become 6000 amp. It's the 2000 plus the 4000. Remember this. If this would goes down the fault from here, this is what we did in a transmission line. It will come back like this if there's a fault. But remember, I'm talking about BusBar fault. I'm talking about the BusBar protection. So now the fault is on the outside, on the external of my BusBar. So what will happen now is, I don't want to trip the BusBar. I want to isolate the fault. So now I have a 6000 goes into here. What will happen into this section into here? Look. The system is in here. What will happen to this system, guys? Remember, I have 20, 40, and then I have 60. I have a 60. This will give me now 60 or minus 60 amps, if you want to look at it from a perspective. Is that clear? Is that clear, guys? Look, pay attention. This will go under saturations. Pay attention. This will go under. The CT goes under saturation. When it goes under saturation, that means XM could go to 0. Goes to 0. So now what I have is I have 60 amp. I have 60 amp going across the 2 ohms. So now I have the voltage under external fault. It's equal to 120 volt for external fault. So what I do now is I go ahead and I set up my relay to operate on 240 volt. Can you see now? I set up my relay to operate, the voltage relay to operate at a double this value if I want. 100% extra. 240 volt I set up the relay. Do you understand the difference between external fault and internal fault? Now, under external fault, I want this and this circuit breaker to trip to isolate the fault. I don't want this to trip. To keep this BusBar live because of the importance of the BusBar. Is that clear? I hope that's clear, guys. Let's now pause because we are going to do a few examples. So this week we are going to focus on the bus bar protection. I hope that's clear. And let us now take a few minutes break and then we come back to do an example together.